I have to apologize. I'm a bit under the weather. But I think we've agreed if I keel over during the talk, Ann Sickles is just going to kick me off the front of the stage, and we're going to go to her talk early, so should be okay. We've got a plan B. The other thing is that since we've been hearing about the history of Phoenix, my own history with Phoenix is that I started on it in, I think, 93 as a postdoc, and by that time, a lot of the stuff that was described by Shoji and Bill had been settled, right? So Phoenix existed. But I remember coming down from MIT as a graduate student and watching some of the earlier stuff. And I mean, maybe I'm just very naive, but it was very confusing, right? We'd watch these presentations by these very accomplished, very smart people. And I don't think there were more presentations than there were IPs at RHIC. So, but if you listen to any one of the presentations, you're like, yep, that sounds great to me, sounds good. And then the next thing we knew, they were all being, I think, welded together, maybe. So Phoenix is 20 years old, and you know, so friends of mine, of course, you know, the people down at the local bodega, they ask me things like, you know, so Dave, how is it that Phoenix has such a nice, successful run? And I'd say, well, you know, it's simple. There's really just one simple idea behind all of it, and that's just upgrades, you know. And as you saw from what Bill showed, I mean, I think it's not that there was ever Phoenix and then upgrades. It's just constant upgrades. Excuse me. And so this was what was on the floor in 2000 for Phoenix. And it's not that there was enough Phoenix there, but, you know, we weren't over-endowed with Phoenix at the time, right? There was just enough to do what we needed to do. And over the years since then, on the right-hand side, I've got a list of various upgrades that have gone in or come out of Phoenix. You can see part of the MVD, the whole south muon arm, this gap right here, the shower max detectors, the NTC, maybe not everybody remembers that one, the T0 counter, the TRD, the FCAL, the aerogel, the TOF West, reaction plane detector, the MPC, the HPD, the VTX, the FVTX, the muon RPCs along with the trigger, DCM2s, JSEB2s, DAC 2010, shielding in the hall and in the experiment, and then, of course, upgrades to the machine itself in luminosity and polarization. So it's this very long series of changes to Phoenix, and it's really different than what you see if you look at a high-energy physics experiment, which tends to have a stable configuration and just accumulates integrated luminosity. I mean, maybe it's because a lot of us come from a nuclear physics background. We always look at little gaps here and think, well, I've got a piece of scintillator and a phototube. I mean, I can put it here and do something interesting with it. And so that's how Phoenix has done its thing, and we're not actually in any danger of stopping that. So this is a little chart from the Phoenix decadal plan. There goes my voice. Which actually turns out to be exactly the same size as the PCDR and the white paper. It's got the same number of references and the same number of pages. There must be some constant of nature there. But what I'm going to describe is contained here, and that's the upgrades and the physics that they'll get to. And so I'm going to concentrate on the stuff that's kind of in the now and into the next few years, and what that will do for us and the kind of capabilities that we'll get out of it. So that includes things like the hadron blind detector, the silicon vertex trackers, the muon trigger, and the upgrades to the data acquisition system. And after this talk, Ann will talk about the farther future. So let me start with the hadron blind detector. Now, this was in and is out now. I know where it is. It's in the high bay in Building 510, happily sucking on nitrogen. It's actually kind of an amazing detector. It's filled with this weird gas, CF4, right, which is both the Cherenkov gas and also the ionization gas for these triple gem detectors at the back. So there's no windows. And it does a couple of nice things for you. Not only does it provide the Cherenkov light and does it do the ionization, it does a couple things you don't really want, like scintillate. And also, if you take CF4 plus H2O, you get HF. So you get hydrofluoric acid floating around inside this thing. So not only does it work well, it's always sitting around, right on the verge of digesting itself. Now, the other thing about it is it worked extremely well. this little formula at the bottom, the number of photoelectrons is determined by some parameters there. This N0, it has a very high value, and I'm not exactly sure if this is the right terminology, but I would say it's the brightest Cherenkov detector that's been built. So it's a very nice detector, and it requires us to run PHENIX in an unusual way with the field on the axis to be as small as we could manage so that you don't disturb the E plus and E minus from Dalitz decay, so you can detect those and remove them. And the point of that is shown here. This is data from, I think, the 2004 run, and the hope is that with the HBD we'll be able to improve upon that. For instance, in this region of invariant mass, E plus, E minus invariant mass, you can see that there's an excess over the contribution from known sources. And looking at that and looking at the widths and shifts of some of the vector mesons, you're looking for evidence of chiral symmetry restoration and various modifications to the properties of those mesons in the medium. Well, here's the difficulty, is that getting out that signal, you're dealing with a situation like this, where the signal to background is incredibly small. So the HBD is there to try and improve the situation by removing a lot of the combinatorial background. Now, even with the HBD, this analysis is extremely complex, and people are working on it and expect results soon. So that's an upgrade that went in, has taken data, and is being analyzed as we speak. Excuse me. So let me move on to heavy flavor. So this is a big focus of the rest of the upgrades. So you saw an example of a plot pretty much like this in Bill's talk. We know a couple of strange things, not only about the light quarks. We know that they show strong flow, and they show great suppression at high PT. But then the weird thing is that we see the same phenomenon when we look at non-photonic electrons. And that's the closest proxy that we have for looking at heavy flavor. So this is the semi-leptonic decays of charm and bottom quarks. And so, excuse me. So it's a very strange thing that these very, very heavy quarks should both flow with the medium and should have their production suppressed so strongly, suppressed exactly, really much to the same degree as the light quarks. So understanding what's going on there gives us insights into all kinds of things about the energy loss and the production mechanisms, the way that these heavy quarks are coupled to the medium. And so we want to be able to identify event by event heavy flavor. And in order to do that, you really need to put in a vertex tracker. So here's a diagram of what the vertex tracker would look like from along the beam axis. So there are a couple layers of very fine-pitched pixel detectors, and then a couple layers, you can see in this kind of complicated arrangement, of what are called strip pixels. And then if you look at this device from the side, so you can now see these are the different layers here, 1, 2, 3, 4. What you're trying to do is determine the distance of closest approach. So you have the primary vertex for the collision, then you have, say, a D or a B meson, which has got a C tau. It's not very large, and you need to detect that displaced vertex, the vertex of that decay is now displaced from the primary vertex. If you can identify that, you can then say, I found the decay of a D meson or a B meson. I've identified open heavy flavor. But you can see it's a pretty tough thing to do when the decay lengths of these mesons are so small, just a few hundred microns. These strip pixels are an interesting bit of technology. It's, I think, kind of worth pointing out something about them here. You want to get XY readout. You want to find out a position in space for these tracks passing through these outer two layers of the barrel VTX detector. Well, you can imagine you could do it either with two layers, one that's instrumented in X and one that's instrumented in Y. That introduces a lot of material. You could try and do it with a double-sided sensor, but that's complicated. So what has been put together with the instrumentation division here at B&L is this kind of serpentine. Each pixel is this kind of winding up of readout, let's say for the blue, get all ganged together in X, the red, get all ganged together in Y, and that gives you a single-sided XY readout. It's a kind of interesting bit of technology. Together with the barrel VTX, you have a similar thing with the F VTX, the forward VTX, these kind of annular detectors at the end of the VTX itself. And these planes here are these blue lines over here, and you're trying to do something very similar. You have a primary vertex for the event. You have then a displaced vertex coming from the propagation and then decay of a D or a B meson into a muon. And if you can identify that, you can then identify heavy flavor in the muon arms. So, excuse me. Doing all of that, again, gives you a lot of handles on physics that we can't currently address with PHENIX. So not only do you identify the heavy flavor that way, but the additional tracking of these FVTX layers before all of the absorber that is the PHENIX central magnet and the front of the muon arm, that additional tracking improves your momentum resolution, and you can do things like now distinguish better J psi from psi prime. Excuse me. And then these things like detecting the B meson through the displaced J psi give you a handle on what's going on with heavy flavor in the collisions. And you can see that ability to distinguish heavy flavor with great precision allows you to distinguish between various models of energy loss and in the medium. And you can see over here with identified heavy flavor, an RAA measurement using the FVTX with reasonable samples of PP and gold-gold data that we should be able to get. You should be able to distinguish between some of these models quite readily. Excuse me. Well, it's, I mean, it's there's a good physics motivation for doing this. It's technically an interesting thing to do. But the other thing that's been interesting to see is just how many people have come together to work on this thing. So you've got, this is the chemistry lab, the VTX lab over in chemistry. You can see you've got people from different universities, different labs working on it. You can see that they're running it a bit like a sweatshop, with people screwing things in all over the place. People get to wear their finest fashion statements in putting things together. And then when they actually get it assembled, it involves yet another contingent of people in PHENIX installing it in place. The detector itself, I mean, it's actually really pretty, right? I mean, this is kind of an amazing thing. Very lightweight carbon fiber structure. You can see some of the layers of the silicon pixels, the silicon strip pixels on the outside. And you can see the FVTX. These are sort of the half annulus as you go out in the extremes of eta. And then all of this gets kind of, there's a matching other half that gets clamped up around a very thin beryllium beam pipe. And all of this, I think you can pick up with your hands. I mean, it's not a very heavy device at all. And really an amazing bit of technology that gives us capabilities that we just don't currently have. A few things you might not know. So Rich Ruggiero can spot submicron deviations with his naked eye. And I'm not sure, but I believe Ming Lu has dropped his car keys into the FVTX. He looks very, very concerned about things. Yuji talked a little bit about this. So this is now fine. So you've got the VTX and the FVTX sit right here. And the FVTX then is to work in conjunction with the existing muon tracker and muon identifier. The idea behind the muon trigger and RPC upgrade is then to add a triggering capability to that so that in, say, the 500 GeV PP program, you can really trigger on high momentum muons and increase the statistics for Ws. Excuse me. So what it consists of are some trigger chambers, these RPCs, and then some electronics to work into a level 1 trigger. I mean, conceptually, it's straightforward. It looks to me like E859, right? It's got just some simple trigger chambers. The thing that's different is just the scale. You can see the scale of these things. They're just enormous detectors, very, very large devices. This is at UIUC. You can see the scale of what's going on. And that's when it's sitting on the floor. The next part of it that's really tricky is installing all of that in place. Now, I don't know if you can quite make out what you're looking at, but if you haven't been in the tunnel, this is the tunnel to the north of PHENIX, it's worth doing. So You can see the RPCs. This chestnut-colored rusty thing, that's the back of the muon identifier stack. And then you can just make out here the edge of the cement wall. So I don't know, there's something like this amount of room into which you have to somehow drop all of these things in place. They had a sort of a practice area set up over at the end of the AGS beamlines where they had set up some shielding blocks with a gap, and the PHENIX technicians and the AGS rigger, or the B&L riggers were practicing, and I think they were having a great time. I think it was something they really enjoyed doing. It was very, very challenging to try and slip all of these devices in place the way they're supposed to be. But you can see that's in place and has already seen some data. Going along with those very large RPCs at the extreme ends of PHENIX are ones that are much closer in. These RPC1s, those are installed now as well. So, excuse me. So those are the bits and pieces of some of the upgrades that you can actually see, you can put your hands on. Some of the bits and pieces that might not be so obvious are the electronics that are associated with that actually read out those devices or make triggers out of the signals from those devices and make them usable and useful. So you can see a couple of things going on. One is that there have been big efforts to try and improve the data acquisition capability of PHENIX. So on the right-hand side in the top, you can see something which shows the live time for PHENIX, so the fraction of time that PHENIX is actually able to take another event as a function of how quickly events are occurring. And no surprise, as you go to faster and faster interaction rates, at some point the live time starts to drop. But you can see that in the difference between how we used to run and how we run now, we've actually improved this significantly. The red circles are higher and kind of keep the high live time out to higher and higher interaction rates compared to how we used to run. What we've done since then is now we've got this VTX in place, and we've read it out. That's another 4 million channels of data to read out. But you can see that in run 11, even with the VTX in place, we've maintained very high live time. When we've run PHENIX in the past for heavy ion physics, we've run a lot of the time we've run a heavy mix of minimum bias triggers, in which case very high live time doesn't really matter so much. But more of the physics program is moving in the direction of rarer and rarer triggers, and so there's more of an emphasis on having this high live time for very, very high luminosity, very high interaction rates. In addition to that, you then have to get all of that high volume of data out of the experiment, and so we have much improved data collection modules and various interface boards to pump the data into the sub-event buffers, a very, very fast network switch in the middle of everything to assemble all the events, and an improved way to pump that out to the buffer boxes that handle everything before it gets sent off to the RCF, where we archive it. So all of those things are upgrades that are either in and out, or planned for the coming run. We then also have upgrades that, as Yuji also mentioned, that are hoped for, may come to pass in the near future here. And one of those is this MPC-EX, this additional layer of like a pre-shower on front of the existing muon piston calorimeter. So this is some layers of tungsten and silicon readout that give us some very nice abilities, very nice capabilities for very low X measurements in the very forward direction. And this is a proposal that, is being vetted inside PHENIX right now. Excuse me. So we have all these upgrades, which give us very nice capabilities, but all of that is aimed at getting out interesting physics from PHENIX. So as far as, excuse me, the VTX, the FVTX, I think are really focused on heavy quark, heavy flavor physics, so probing the strongly coupled quark-gluon plasma with these heavy quarks as a very different kind of probe than the light quarks that we have been using so far. One thing I didn't really mention, but this is another upgrade, I guess you'd call it that, of the machine, which is the ability to collide very different species than we have used so far as a way of varying and controlling the geometry of the collision. In looking for the QCD critical point, we've run the machine at much lower energy, and now some of the things like the large acceptance in the mid-rapidity region of the VTX may be something we can take advantage of to look for more kind of general features of the data. The upgrades that give us better capabilities in the forward directions, either the muon trigger and RPC upgrade or this MPC-EX, give us acceptance at very, very forward angles, which gives us access to very low X partons in the nuclei or in the nucleon, and give us access to kind of different phenomena that we can study. The muon trigger and RPC also gives us this ability to collect larger samples of Ws, which gives us a handle on the flavor separation of the flavor decomposition of contributions to the nucleon spin. Again, something that's touched on by UG. Excuse me. So I talked about these upgrades right here in this kind of near term, and the physics that they get at is, again, something I just mentioned and is kind of circled up there. So chiral symmetry restoration being addressed by the HBD, the beam energy scan and critical point search is sort of the low energy running of RHIC. The tagged heavy flavor and charm and beauty is something where the VTX and the FVTX really make a difference. And then the spin flavor structure through the W goes to either the electron in the central arms or muon in the forward arms, excuse me, is a big part of that. So I think what you're seeing is something which is continuing a very fine tradition of PHENIX upgrades, right? This is something we have done since day one. It's something which, this I think is a good point, that it's really driven by compelling physics interests. But because the lead time on some of these things is so long, people have had to have a very good guess very far ahead of time about what will be a productive and useful thing to go looking for. The upgrades we have in place give us really exceptional new capabilities. And I think this is something we need to really, Bill talked about knowing your competition. I mean, in some of these things, our competition is LHC experiments, right? Having the ability to do identified heavy flavor is something that I think is, we're severely handicapped without it. So it's very good to have. I hope that some of the pictures showed you that there was really a huge effort across the entire collaboration getting these things in place. And I think, well, okay, maybe it's apple pie, but I think it points to years of great physics to come for the experiment.